Okay, we want to look at another problem that we worked on in class Friday that also caused some problems. And the situation looked like this. We had two masses, and mass 1 was pressed up against mass 2. And the question asked, how hard did you have to push on mass 2 so that it didn't slide down? So just so we're clear what's happening here, if mass 1 and mass 2 weren't accelerating, if there was no horizontal force on them, I should say, well, it's pretty clear that mass 1 would just slide down and hit the ground. And what the problem is saying is that if I push on mass 2 hard enough, then they'll accelerate, and as mass 2 pushes against mass 1, if there is friction, that can prevent mass 1 from falling. So to understand what's going on here, let's take a look at the free body diagrams where we should start all of our Newton's second law problems. And we're going to assume that mass 1 isn't falling, as the problem stated, and think about what forces would be on there. Well, of course, there's the weight pulling down on mass 1. But if the two objects are accelerating, that means that mass 2 is pushing against mass 1 to cause the acceleration, so there's a normal force from mass 2 on mass 1 pointing to the left. And there is also going to be a friction force. And the friction force, the size of the friction force, is going to be proportional to the normal force. So if the normal force isn't very big and there's a small acceleration, the object would still slide down, m1 would fall. But as you push harder and harder and n21 becomes bigger, the friction force also becomes bigger, and eventually the friction force can be large enough to counteract the effects of the weight. And that's why the object would accelerate horizontally, but vertically can stay in place. Thinking about the forces on mass 2, well, there's the force that you're pushing with, F, and there's its weight. And because mass 2 is applying a force to mass 1 through the normal force, there's going to be the Newton's third law pair of the normal force from mass 1 on mass 2. And there's also friction between mass 1 and mass 2, which acted up on mass 1, so it must act down on m2. Finally, mass 2 isn't accelerating in the vertical direction, so there is a normal force from the floor counteracting the weight and the friction force from mass 1. So we have those forces. And in fact, this includes the answer to part A, where it asked what forces are acting on mass 1. Well, it's the forces that we've drawn here in our free body diagram. So the next step, after we have our forces on the free body diagram, is to get the x and y components of each of those. So we'll need to make a table, and we can look at each force on each object. And for example, the normal force on object 1 has an x component that's just equal to the normal force and a y component of 0. The friction force is equal to 0 in the y direction because the friction is going to oppose the motion between the two objects. And mass 1 was going to slide down mass 2, so the friction force points up. So it has a y component of mu n21. And here we're talking about static friction, so I should have written mu s times n21. And finally, the weight is in the negative y direction. And we can do the same thing for the forces on mass 2, and we get a table that looks like we see on the right there. And the reason that we do this table is that we now want to use the equations that are given to us by Newton's second law, that the sum of the forces is equal to the mass times the acceleration. So the sum of the forces in the y direction on mass 1 are mu times the normal force minus the weight, and that's going to equal 0 because there's no acceleration in the y direction. And the sum of the forces in the x direction, well, there's only one, it's n21, and that's going to equal the mass times the acceleration. Notice that I did not use a1 and a2 because the acceleration of the two masses are the same, so there's only one acceleration. So when I look at the Newton's second law equations for mass 2, I'm going to have in the x direction f minus n12 equals m2a, and that's the same a that we had for mass 1. So now it's just a matter of solving these problems, solving these equations that are given to us from Newton's second law. So if we look at the y component on m1, we see that mu times n21 minus m1g equals 0. Well, that just tells us that the normal force is m1g over mu, and that's equal to 34.7 newtons when we plug the numbers in. This is actually the answer to part C of the problem that asked us to find the contact force between mass 1 and mass 2. Looking at the x direction, the sum of the forces in the x direction is equal to the mass times the acceleration, or the acceleration is just equal to that normal force divided by the mass, because there is only the one force, and we get 34.7 newtons divided by 2.3 kilograms, and we get 15.1 meters per second squared. We can use this in conjunction with our Newton's second law equation for mass 2 in the x direction. It says F minus N12 equals M2A. Well, we know N12 because it's the same as N21 by Newton's third law, and now we know M2, and we know the acceleration. Plugging all of this in gives us a force of 113 newtons, which is part B from the problem. And finally, it asked us what the net force on mass 2 was if we were applying exactly this much force, and we would get 113 newtons minus the normal force of 34.7 newtons, which is 78.3 newtons. So this problem isn't so bad. Again, we just do the same thing that we've done in the previous problems, where we have a schematic and understand what's going on, draw a free body diagram, use the free body diagram to construct a table with the x and y components of each forces, and then use that to help us work through Newton's second law.